Okay. Can you all hear me? Is this switched on? Yeah? Brilliant. Okay, yeah, at the back. Yes, nice one. Good afternoon, everybody. I'm going to start right away because I've got quite a full schedule to go through and I don't want to be dragging out over my time. So I'm going to start now, even though the doors aren't closed yet. My name is Mark West and I'm here today to give you a practical-ish introduction to data science. The reason I call it practical-ish is that, to actually work with data science and machine learning, you need to understand some of the theory behind it. And what's difficult with a talk like this is pitching it at the right level. So some of what I talk about today, you might already know about, but I hope that you'll all get at least something out of it. So who the devil am I? Who is this Englishman? I'm a recovering Java developer. Oh, that's not looking good, is it? I don't know what happened there. But yes, I'm a recovering Java developer and architect. I've been working with Java for about 20-odd years. And in the last year and a half, I've been building up a team of data scientists at my employer, Bouvet, in Oslo. So I'm coming to you today from the perspective of a developer who's come into machine learning and data science. And in my spare time, oh my God, what's happening there? Look at that, that's very odd. But in my spare time, I'm actually the leader of JavaBin, the Java user group. So that's why I have this weird t-shirt on. So I don't know what's going on with these presentations, so I'm just going to stop it and try and see if I can get it to look a bit more pretty, because that doesn't look good, does it? Let me try that again. Right, that's better, isn't it? Okay, so what am I going to talk about today? This is the agenda. I'm going to start by defining what data science is. I'm then going to run through some basic machine learning algorithms, and then at the end of the talk, I'm going to give you a practical example, show you data science in practice. And so to start with, what is data science? Well, when you want to know what something is, what do? You go to Wikipedia, right? That's what I did. And Wikipedia gives me this great quote saying that data science is an interdisciplinary field of scientific methods, processes, and systems to extract knowledge or insight from data. Yeah, that's great. But what does it mean? Right? We have to drill down into this a little bit to get a better idea of what data science is. The first thing I want to drill into is the word interdisciplinary. What does that mean? Well, I reckon that most people in this room are working on the boundary between, domain knowledge and computer science. You're using your computer science skills to create software based on the domain knowledge you've got from your employer or your client. I would argue data science requires an extra kind of area. It requires knowledge in mathematics and statistics. And that's because the machine learning, which is one of the main tools of data science, is basically applied statistics. A lot of people may not agree with that, but that's my opinion on it. I believe that when you're working with machine learning, there's a lot of mathematics, stats involved in it, and you have to understand how these things work. So it means to find data scientists is quite difficult. People that have all of these things is difficult. It is very, very difficult. But if you're a computer scientist, if you invest some time building up your knowledge around math and statistics, then you can actually get into data science quite easily. The next word, scientific. What does that mean? Well, data science is science, right? It's a scientific method. And the process for data science looks pretty much like this. You start with a question, a hypothesis, something you're going to try and prove. Can I get this car to drive itself? Can I recognize people's faces when they come into the building? That kind of thing. When you have that question, then you're going to gather your data. That takes time. You have to go to all your system owners and say, can I have access to your database? They're like, what do you want it for? That can take an awful lot of time to get your data and get it into a form that you can actually work with. The next step will then be to mess around with the data. Start rolling up your arms, messing around with it, doing some simple analytics of the data to see how it hangs together. These first three phases are 60 to 80% of the data scientist's job. A lot of people think that data scientists work just with machine learning, but they spend most of their time massaging the data and forming it into a form that they can work with. When you have actually done your exploratory data analysis, you understand how the data fits together, then you can choose the right algorithm. You can actually build a formal model. And a lot of people, what they do is they just try every possible type of model for their data and just see which one gives them the best results. That's not the right way to do it. You need to choose the right algorithm for your use case and for the data you have. Once you have your model, the results that you get from it may not be what you expect. You may have to interpret them. And then you're going to have to explain them to the pointy-headed boss who gave you this job, right? You're going to have to explain what you've done in a language that they can understand. And then, you profit. You're finished. Now, this is the basic data science or data science process. And if you look at CRISP, DM, or Microsoft, they have their own team data science process. They all have these steps in them. And the other thing to remember, this is an iterative process. It's not necessarily sequential. You might get to step 3, start exploring your data and realize, oh, my question's wrong. I can't answer this question, or I need more data. Then you have to go back to steps 1 and 2. But there's something missing here. How do you get this into production? Right? That's often when you're working in machine learning, people get so excited about the machine learning part, they don't think about how they're going to get into production. And I would argue that to work with data science, you need different roles. So you have your data scientist who creates their algorithms and does all of the data wrangling and that kind of thing, defines hypotheses. But you're going to need a data engineer. You're going to need somebody who gets this algorithm, puts it into production, operationalizes it, monitors the algorithm to make sure the output of it is good, and all that kind of stuff. So you need a data engineer. And there's also a very good chance you're going to need somebody to visualize your data. There's an old saying that every picture says 1,000 words. If you can get a complex set of data and visualize it in a good way, an intuitive way, you can actually get your message across to your customers or your employees a lot easier. And of course, you're going to need a project manager, but not just a standard administrative project manager. You need somebody who understands the data science process. Someone who can go to your stakeholders and say, this is going to take time. Right? You need somebody who's going to go around the company and evangelize what you're doing and try and create some momentum for data science in your organization. Now, it doesn't mean you need 4 people in every project, but these are 4 competency areas that I think you should have when you're working with data science. So back to the quote, that I started off with. Data science is about extracting knowledge or insight from data. So let's address the elephant in the room. Is data science just BI? I mean, there's a lot of people who think it is. And it's a fair thing. You're working with numbers, you're working with data. But I would argue that data science isn't a rebranding of BI. It's an evolution. It's the next logical step. And if you compare data science and BI, there are some areas where data science builds upon BI. And here's some examples that I actually found when I was first getting into data science. I found these in the blog on LinkedIn, and I actually think they're pretty good. So if you compare business intelligence and data science, one of the ways in which they differ is the data sources. Business intelligence generally works with data warehouses, structured data, schema on write, whereas data science gives you the ability to start working with your unstructured data, with your log files, your audio files, your images. Business intelligence often is about visualizing your data and using statistics to kind of, to steer your ship. But data science also adds the ability for machine learning. And the goals of BI is, as I just said, strategic decision making. Whereas data science can give you the ability to actually, create your self-driving cars or your facial recognition or your voice analysis. So machine learning then. It's a tool for data science. People get confused about what machine learning is. What is machine learning? They talk about AI, they talk about deep learning, and I got very confused about this. What is what? So the way I like to look at this is that AI, general artificial intelligence, is a very broad field. It's as much about philosophy and psychology as it is about computer science. What is intelligence? The Turing test. How can you prove that something is intelligent? What about how our own brains work? All of this kind of stuff isn't computer science. It's a broader kind of general artificial intelligence field. So I would argue that ML, or machine learning, is a specialization of AI, which is about applied statistics. So you use algorithms to let your computers learn or describe data without you actually having to program them. And then where does deep learning fit into this? Well, deep learning is a specific type or a specialization of machine learning. And basically, deep learning is like stacking algorithms. Deep learning is neural networks. So you have lots of algorithms stacked on top of one another. Deep learning is advanced. It's very much the bleeding edge today, so I'm not going to be talking about it anymore. I'm going to be focusing on more simple machine learning algorithms, because I think the biggest mistake people make with data science is they say, right, I'm going to do machine learning. Let's get started with TensorFlow. And you don't need to get started with TensorFlow. You can do simple machine learning, with Excel if you really want to. Not that you would want to, but you could. It's just an idea. So, okay, I'm at the end of my first part of my talk now. So just to reiterate a couple of things. Data scientists require math and statistics skills in addition to computer science. Data science is hypothesis-driven. Data science projects require a range of competencies and roles, not just a data scientist. If you're going to do a data science or machine learning project, you can't just hire a data scientist and they'll fix everything. Because a lot of the times, it's a secret between me and you guys, but a lot of the times data scientists produce really crappy code, right? You need somebody to fix it. So you're going to need more than just data scientists. And, don't get too hung up in the difference between data science and BI, but you can see data science as an evolution of BI. Okay. Machine learning algorithms. Here, I'm not going to go into complex algorithms. I'm going to talk about very simple algorithms, because as I say, this is an introduction. But just to remind us what machine learning is about. Machine learning is allowing computers to find the correlation between data and the desired label. More or less, especially if you're talking about supervised learning. So in the old days, or not in the old days, but what we do now is we as developers, we have our data, we look at our data, we write rules based on our business knowledge, and we feed the data and the rules into our system and it gives us output. But with machine learning, you give the data and the output to the machine, and you allow the machine to find the correlation between those two. And then the machine will give you the rules. I forgot to mention at the beginning because my slides started messing up. At the end of this talk, I'm going to publish my slides on Twitter. So there's my handle there. So I'll put them out on the hashtag JFocus. The JFocus hashtag, just so you don't have to take pictures. Unless you're taking pictures of me, and that's fine. That's completely okay. But anyway, when you're working machine learning, you need to think about what kind of model do you want and how you want the model to be. And I like to think that models should be relatively general. So imagine that you're going to create a model that can look at a picture and it can tell you whether that picture contains a sheep or not. What you're going to do is you're going to train that model with lots of pictures of sheep. Black sheep, white sheep, all different types of sheep to try and allow your model to find the correlation between what a sheep is and the features that sheep have in common, right? So ears, tail, 4 legs and whatnot. And what you want is like an internal representation, which isn't unlike this, like a child's drawing, which captures what a sheep is. I can show that to anybody, and I'll know what a sheep is. But if you're not good at training your model, if you give your model bad data or you don't give it time, you're going to end up with something like this, which is the model isn't able to find the relations between what a sheep is and the label sheep. You can go the other way. You can overfit your model. So your model actually memorizes the pictures you've shown it. And then it hasn't actually learnt. It hasn't learnt the correlations between the features and the labels. It's just learnt to actually memorize the pictures you show it. So if you show it new pictures of sheep, it fails. So what you're looking for is this happy medium in the middle. And what's right for your use case will go a little bit backwards and forwards depending on what you're trying to achieve. But often when you're working with this kind of problem, you're going to have to accept a certain amount of error. So machine learning comes in 3 basic types, right? You have supervised learning. Supervised learning is just like what I just talked about. You show your algorithm a picture, for example, of a sheep and say, this is a sheep, and that's it. You allow your algorithm to learn the correlation between the label and the features. And for another example of supervised learning might be face recognition, or even predicting house prices based on historical data. Another type of machine learning is actually unsupervised learning. And this is just about describing your data. So you feed your data into the algorithm and say, please tell me about the patterns you find in this. An example of that could be giving your customer data to the algorithm and letting your algorithm find the natural groups of these customers, the natural customer segments. And the third type of machine learning is reinforcement learning. This is where it's all sexy. This is where you have an agent, basically, who's learning from their environment and adjusting their strategy to be better at whatever they're supposed to be doing. So reinforcement learning is often used for game playing, or even stock trading, that kind of thing. Again, reinforcement learning is a bit advanced, so we're not going to cover it today. We're going to go to the simple stuff. We're going to focus on the simplest supervised and unsupervised learning machine learning algorithms. We're going to look at regression, which is about predicting a continuous value like a house price or an age. We're going to look at classification, which is about predicting a class. So, for example, is this a picture of a sheep or a cow? And we're going to look at clustering, which is about grouping your data based on its natural parameter or its natural patterns. And these are the algorithms I'm going to look at, which are very, very simple. Linear regression is very, very simple. So simple, a lot of people don't call it machine learning. Decision trees, which is basically what you guys do every day. You build decision trees in code. And k-means clustering, which is possibly my favorite machine learning algorithm because it's just fun and easy to visualize. So linear regression. We all know linear regression. We all did this at school in maths, right? I mean, linear regression is pretty simple. So imagine I have a simple data set here. And what I want to do is I want to create a model that predicts the value of a house based on its floor space, right? So what I do is I get all this fantastic historical data with my feature, which is the floor space, and I want to predict the house price based on that. So I take my historical data, I plot it, and I draw a line through it. And that's it. That's your machine learning. The line itself is your model, right? And this model is basically a trend line. And based on this trend line, we can actually use it to predict new house prices. So we can say, like, okay, if we have a house which is 5,000 square meters, based on our historical data, it should be worth around about 1.5 million or something like that. But of course, this is nonsense. This model is useless. I mean, like, you can see, for a start here, we have a deviation. This could be an outlier, or it could be a deviation that tells us our model is useless. Our model is useless because we're trying to predict house prices on one feature, the size of the house. We're not thinking about the location of the house. How many bedrooms does it have? What condition is it in? Does it have a toilet? Does it have running water, right? All of that stuff we're not paying attention to. So this is the oversimplistic model. But I just wanted to show you that linear regression, I mean, this is machine learning, and this is very, very simple. So how does linear regression find this blue line? How does it actually find this line? It uses an algorithm called ordinary least squares. And basically what that's doing is it's going to draw a line between all your data points, and it's going to measure the distance each data point is away from the line, square it, and add them together. And this is what is called the sum of squared error. And what linear regression tries to do is reduce the sum of squared error by moving the line, the fit, up and down to try and reduce the sum of squared error as much as possible. So that means that this kind of algorithm is very prone to problems with outliers. An outlier could be like a one-off in your data set, or it could be an error in your data set. And outliers will drag your trend line away from where it should be. So you always have to look out for outliers and have a strategy for dealing with them. And that could either be deleting the records of outliers or finding some way of normalizing them. So that's linear regression. Really, really simple to understand, transparent, especially if you're just working in 2 dimensions, easy to plot and visualize. Outliers will skew the trend line, and it doesn't work well with nonlinear relationships because it's linear regression. If you want to model nonlinear relationships, you need a nonlinear model. The next algorithm I'm going to look at is decision trees. Decision trees are just about calculating the best split. Now, do you guys get rung up by British recruiters? Yes. I'm so sorry. It's like British recruiters and Brexit are the 2 things I'm most embarrassed about. I'm actually applying for a Norwegian passport now just so I don't have to be, bunged in with these people. But anyway, imagine that a bunch of British recruiters ring me up and say, Mark, we need your help. Do you know any J2EE? No. Mark, we need your help. We want you to create a model for us that tells us who should get a pay rise. And here's some historical data. So here's all of the names of the British recruiters. And we have some features. We have, like, did they make a placement? Did they actually get a person out on site? Did they actually manage to sell a person? Have they received any customer complaints? And have they ever lived in Norway? Because most British recruiters I've spoken to have never lived in Norway, know nothing about the culture. And anyway, then we also have this last bit of information here. Did they get a pay rise or not? So we have our features, we have our labels. Now what a decision tree does is it tries to find the feature that best splits the labels. So I have a binary result here. Either they got a pay rise or didn't. If I try and split my data based on whether they lived in Norway or not, you can see I don't get a very good split. If I split my data on complaints, again, I don't get a very good split. I've got both people who got a pay rise and didn't get a pay rise on both sides. But on placements, you can see that I have a perfect split. So this is a really simple example of a decision tree. In this case, I would actually, or the algorithm would split my data on placements, whether somebody made a placement or not. But what happens when you have bad data, when you have shitty data? Imagine the data told me, basically, that, yeah, so this is how it should be. But imagine the data told me that, like, everybody who had got a complaint also got a pay rise. Then I would actually have given them a model that gave pay rises to everybody who got complaints. And I actually think that's how British recruiters work. But you can see that your data can really cause problems. That's another thing you need to know about. That's why math and statistics are important. Because if you have crappy data or even bias in your data, it's going to give you a bad model. I can give you a good example about this. Amazon had a model which they used for hiring people. Have you heard about that one? The one that was biased against women. So if you sent in, if you're a woman, and if your CV actually contained the word woman or women, I think you actually got thrown out. That's the danger of using AI for automation. So you always have to look at your data. It's not just about running a machine learning model, but you have to look at the quality of your data. Now, what happens if your decision tree can't, or your data can't be split on one feature? Then you have to recursively partition. And this is a kind of 101 data set from machine learning, where shall I play golf or not, based on these features, the outlook, the temperature, the humidity, and the wind. Now, if I feed this data into a machine learning algorithm, a decision tree algorithm, the first thing, the feature it's going to split on is outlook. And that's because every outlook record that is overcast says play golf. So the next step is to find the next feature to split on. So what will happen is for all the records that are sunny, we're going to try and find a feature that best splits the data. And there we find that humidity is the best. And then we do the same for rain. What's the best feature there? And we find that wind is the best feature. And then we're finished, because we've actually got to the point where all our leaf values are like homogeneous. So that's basically how decision trees work, recursive partitioning. And they can either stop when you get to the point where all of the data points, the endpoints are the same, or you can actually say to your tree, I don't want you to be any deeper than so much, because the danger is if you let the tree just grow and grow and grow, it will carry on growing and growing and growing, and it will actually be overfitted. It will be very specific to your training data and not generalized enough for new data. So that's decision trees. White box, easy to visualize, flexible, robust to outliers, and are good for nonlinear boundaries. But they are very susceptible to overfitting, and changes in the data where you slice the data can actually give you very strange results. Now, if you're going to work with decision trees, I would definitely advise you to look into random forests, because decision trees are very prone to overfitting to your training data. So if you use random forests, they're like another algorithm which is similar, which constructs lots of decision trees and then puts them together, aggregates them together to give you a good result. The last algorithm I'm going to talk about today is k-means clustering. This is an unsupervised learning algorithm. This is great for finding patterns in your data. This is one of the first algorithms you will generally use in exploratory data analysis when you're trying to find out how the data hangs together. And k-means clustering is about finding k. How many clusters are you going to try and find? That's what the k stands for. And the amount of clusters you're going to look for need to be enough to give you meaning. And but also small enough that your clusters are distinct from one another. I guarantee that everybody in the room knows how many clusters are in this data set here. Anybody want to say? 3, right? It's obvious. Now we're looking with millions of years of evolution and a lifetime of training. So we can look at that and we can say that's 3 clusters. But if that's just a set of data which you give to a computer, how is it going to be able, or she, sorry, or it even, going to be able to find the natural groups? How do we calculate k? We need to find a programmatic way to do it. And there are different ways of doing it, but I'm going to show you a way which is very easy to visualize, therefore easier to communicate. So we use the sum of squared error. Now, if you remember the sum of squared error, it's about measuring the distance that each data point has from a trend line, or in this case, the center of a cluster. So we measure the distance each data point has to a center of its cluster, we square them and add them together, and we get the sum of squared error. And that's the same as we did with linear regression early on, if you remember. Now, how sum of squared errors work with clusters is quite interesting, because basically, the more clusters you have, the lower the sum of squared error will be. And to show you that, if this is my data set and I separate it into, oops, something happened there. Oh no, I think that slide's been deleted, sorry. Okay, I don't know what happened there, but like a slide got deleted last night, probably when I was drunk, I don't know. But like, basically what I'm trying to say here is that the sum of squared error is actually related to the amount of clusters you will have. So basically the more clusters you have, the lower the sum of squared error will be. And what you're trying to do when you're looking at the sum of squared error, oh, I see what's happened there. I just have to hop, there you go. If I actually set 2 clusters to that data, I would then be measuring the distance from each blue spot to the center, right? And if I set it to 4 clusters, the distances between my data spots and the center becomes lower. So the sum of squared error gets lower. And if I plot my data against the amount of clusters that I apply, so that data I showed you at the beginning with 150 data sets, which was 3 clusters, what we find is if we plot them against each other, the sum of squared error to the number of clusters, we see that at this point here, we get like a sharp bend in our graph. And that is actually how we calculate or can visually calculate the right number for k. So this is actually what's called a scree plot. So I don't know why that slide earlier on, that like just popped in the middle there, but we'll see. Let me just go back to that. I'm just going to fix that so I can actually go through this properly with you. So I don't know what happened there. It must have been, let me see, that's iteration 2. So that needs to go down there, I think. Iteration 2. That's iteration 1. There we go. And then I can just do this in proper order. So I do apologize for that. This is live coding with PowerPoint. Right. So assuming we've got our plot, our optimal value for k, which is 3, how do we actually apply it to the 150 data sets or data points that I showed you just before? Well, the first thing is the algorithm will actually plot 3 centers randomly in your data, right? It will then measure the distance from each data point to the center of a cluster and allocate each data point to the nearest centroid. So it allocates cluster membership based on distance from the centroid. But then what happens is we'll see our centroids are not at the center of our clusters, so we have to move our centers to the center of the cluster. Then, of course, we have to reallocate membership, and we have to move the data points to the center of the cluster again, and we carry on doing that. And with this data, after 6 iterations, this is actually a real data set which I implemented k-means on. After 6 iterations, our data sets or our clusters stabilize, and we have 3 clusters. And that's basically k-means clustering. Now, as you can see, k-means clustering is actually very, very fast. It's a very easy thing to get started with. But it works best for spherical spherical data sets. So in other words, if your data naturally falls into spheres, then k-means is good. But if your data naturally falls into different shapes, then k-means clustering might not be the right one for you. The other thing is that data points in k-means clustering can only belong to one cluster. So, key takeaways. The first key takeaway is never update PowerPoint after drinking. That's the first. And then the second one is that there's 3 main types of machine learning: supervised, unsupervised, reinforcement learning. Machine learning is more than neural networks. I've shown you 3 machine learning algorithms. I haven't mentioned neural networks, right? Don't fall into the trap of going straight to TensorFlow. There's often a lot easier way to solve problems than going straight for neural networks. Neural networks are brilliant. Deep learning is brilliant. But start with the simple stuff before you start upgrading to the more complicated stuff. A good model will need to find the balance between overfitting and underfitting. It needs to be generalized, not too specific, not too loose. And then just remember that algorithms are merely tools. Your machine learning algorithms are already implemented. You just feed your data into them. What you need to do as a data scientist is make sure your data is good enough for your machine learning algorithms to give you value. All right, so on to a practical example. And the danger when you're going for a practical example, excuse me, I'll just get some water. The danger with practical examples is often you can spend a lot of time explaining the domain and trying to explain what you're trying to model. So I chose a domain which is really easy, that everybody knows already. Who's seen Titanic? Hey, right. I didn't ask if you liked it, but like, you know, everybody knows about Titanic, right? Everybody knows about Titanic. It's like, it's folk knowledge, it's common knowledge. So what I'm going to do today is I'm going to build a model predicting survivability of the Titanic, and this is a well-known data science problem. You can get the Titanic data set on the web, and it's very well known. Lots of solutions to it. My hypothesis is that you can predict survivability on the Titanic based on 3 variables: age, gender, and ticket class. And the reasoning for my hypothesis, well, age and gender is like women and children first. That was like, a big thing. The other thing, the third thing, ticket class, is based on me watching Titanic and seeing that Leonardo DiCaprio, who was in third class, drowned, and Kate Winslet, who was in first class, survived. So this is what the data set looks like. These are the variables that I have. And I'm really only interested in the survival, which is a 0 or 1, the ticket class, which is 1, 2, and 3, 1 being first class, obviously, which is the best, and the third being third class, which is Leonardo DiCaprio. Gender, which is currently set to male or female, and the age in years. And that's what I'm going to use to build my model. I'm going to build a decision tree. And the tools I'm going to use something called scikit-learn. Have you heard of scikit-learn from before? Yeah, there's a few heads nodding. Right. Scikit-learn is awesome. It's basically a free Python kit which has lots of machine learning algorithms implemented. It also includes other Python libraries such as NumPy, which is great for maths, pandas, which is great for data sets, and matplotlib, which is great for data visualizations. I'm going to be showing you the code in the Jupyter Notebook, which is a great tool for showing code and visualizations. It's not necessarily, if people say they've got a Jupyter Notebook and they want to put it in production, I'm not sure. I'm not sure Jupyter Notebooks are a good way of creating production level code, but they're a great way for sharing code with people. And because these things are a pain to download and get the right versions and everything like that, I always use the Anaconda distribution. This is a single distribution you can download. It includes Jupyter Notebooks, scikit-learn, it includes VS Code, loads of other stuff you can use for your data science projects, all in one download, making life a heck of a lot easier. So I'm going to move over to my Jupyter Notebook now. Let me see, where are you? There you are. Now I'm going to have to zoom in and out of this quite a bit, but you can see this is my Jupyter Notebook. I'm not going to, you can see all the stuff in here with plots and all kinds of stuff like this. So we're going to go through all of this. So let's put it into presentation mode. Right, so the first thing I'm going to do is I'm going to import my data set. I have my data in a CSV file, and I'm going to use pandas, and that's just basically running a simple line of code, read CSV. It's very, very simple. And then I'm actually just displaying my data set here. And if I just scroll in a little bit, you can see there's all these names, the gender, the age, the amount of siblings and spouses on board, parents and children, all that kind of stuff. First thing I notice when I'm looking at this data is there's a few ages that are nan, right? So this data is missing a few ages. So I'm going to do some very simple statistical analysis. I'm going to do a describe, and the describe will take all the numeric data in my data set and give me things like the count, the mean, the standard variation, all that kind of stuff. All that kind of good stuff. Now if I just scroll up a little bit, I can actually find out quite a lot of information from this. I can see, for example, that I'm missing a whole load of age values. I've only got 714 age values, and I have 891 records in my data set. I'm missing 177 age values. That's the first thing I notice. The second thing I notice is that the mean for survived is 0.38, which tells me that 38% of my data set actually survived, because survived is set to 1 if they survived and 0 if they died. Right, so the next step is actually do something with this. I'm going to do something called feature engineering. This is something that data scientists do a lot. Feature engineering is to take existing data and create new features based on that data. And this is one of the most important things you'll be doing as a data scientist. This is one of the things you'll be spending a lot of your time getting right. So what I'm going to do, I have a hypothesis that, because I have all of my names, I know I have names for all of my data, and each name contains an honorific. The honorific is like Mr., Mrs., Sir. So what I'm going to do is I'm going to calculate the median age for each honorific, and then use that age to replace the missing age values. And very, very simple. So the first thing I'll do is I actually create a new feature called honorific, which is actually this last column here. And all I've done is I've just tokenized the name and just taken the honorific out. So that's very simple. The next thing I do is I'm going to see how many honorifics I have. Scroll in here. So we can see actually my data set is, it's not very well spread out. I have 517 Misters, but I also have things like Don, John Keir, the Countess. You know, lots of strange names here. So I'm actually going to normalize these a little bit, just to make the life a bit easier. And what I'm going to do is I'm going to do this mapping here. So basically, captain, colonel, doctor, major, reverend will all become servicemen. They'll just be grouped together. Then I will get a better median age as well, because I'll have more data to aggregate. Don becomes sir, because that's Italian for sir. John Keir apparently is Dutch for sir. Is anybody Dutch in the room that can verify that? That's what I found on the web anyway. So I'm going to add Don and John Keir to the sir group. Mademoiselle becomes Miss. Madame becomes Mrs., and so on and so forth. So I'm going to reduce the amount of honorifics. And I'll do that mapping, and then I'll just do a simple box plot. Now, this box plot is going to show us a couple of things. Just zoom into it. There's a box plot of all of my data. The first thing it shows us is that I've got less honorifics now. I've got lady, master, miss, Mr., Mrs., serviceman, and sir. And this box plot is showing me the distribution of age for each group, right? And you see these dots at the top, they're outliers. But what we're interested here is the green line. The green line tells us the median age. Now, if anybody here is colorblind and can't see that, or you know, the mean line is just going through the middle of each box. So with that, we actually start to get an idea what the median age for what each group is. We see that lady is around about 40-something, master is about 7, Mrs. 22, Mr. 30, Mrs. 35, serviceman around about 50, and sir around about 40. So with those median ages, we can then replace all the missing ages that we had. Okay, you guys with me on that? So what we do is we calculate the missing age for each honorific group, and then we use those median ages to replace the missing ages. So that's that done. The next bit of feature engineering isn't really feature engineering, it's just a fix, because my sex variable is a categorical variable, and it's actually currently set to male or female. So what I've done is I've run some code here which actually changes it now. So male is now set to 0, and female is set to 1. And now we've actually got to the point where we can start looking at our data. Does our data reflect our hypothesis? We can do some simple graphs to get an idea if it does. The first one is plotting the class against survival. So what we see here, and these are just counts. So what we see here is that if you're in first class, survival, the amount of people who survived, which is 1, is higher than those who died in first class. And if you look at those who are in third class, you see, oh, you're really stuck. You're in trouble, right? If you're in third class, your chances were not good. Whereas if you're in second class, 50-50. So the data actually reflects my hypothesis pretty well here. What about gender then? Sorry, gents, bad news. If you're a man on the Titanic, your chances of dying were somewhat higher. We can also say, though, that if we look at our data set, 517 of our data set were men. Right, so it skews our data a little bit, so we have to kind of take that into account. But we can see here, at least the data that I have shows me that men had a higher proportion of deaths against survival than women. And the final one is age. Age is a more difficult one to plot, because age is a continuous value, it's not binary. So what I had to do is I had to first split my data into adult and child based on how old they were. So basically, I think it's, let me just look at my data, yeah, anybody over 14, so 15 and upwards were classed as adults in my analysis here. So what we see here is something, this isn't actually what I expected. We see that with children, it wasn't that big a difference between death and survival. And then I got to thinking about it, and I think that class actually has a very big factor here, because like a lot of people traveling in third class had children with them. A lot of people in third class died. And if you're a small child, if your parents died, you died. This is a sad fact, but so I think that the link between age and mortality isn't so simple. I think that class and gender have a bit to play in there as well. So I'm going to actually carry on. I'm going to make my decision tree. Get rid of all the features I don't need. I don't want them in my model. So all the stuff like name, ticket, fare, cabin, that's all going. I just want the simple stuff. And I end up with this. I end up with whether they survived or not, the class, the sex, and the age. So now I'm ready to build my machine learning model. The first thing I'll do is I'll split my data into features and labels. So the label is whether they survived or not. The features is age, class, and sex. Simple as that. And I split my data into training and testing sets. This is really important. This is really important because you have to remember that you should never test your model with the same data you trained it with. Because if you do that, all you're doing is like checking if your model remembers what you've given it already. What you need to do is give your model new data and see if it still does a good job. So I'm taking 25% of my data out, which is going to be put aside for testing the model after it's built. And now I'm going to do the machine learning bit. We've been waiting for this. You've been waiting for this for 40 minutes now. Right, okay, let's go. There you go. It's like this machine learning algorithm is already written. You just run them. Your data has to be in good form before you run them. Now, in this particular case, I'm running a decision tree classifier. And all of these values that are set underneath, they're all the default values. I'm not setting any hyperparameters. You can tune machine learning algorithms. That's called hyperparameter tuning. But I haven't actually changed any of them here. I'm just running it as is. So let's have a look. Let's test our model with the testing set. And we see that with our testing set, we actually get 74.88% accuracy. So that was it. Now, a lot of the reason I got the better accuracy or good accuracy was because I've already massaged my data, I've worked with my data, but also I had a good hypothesis. If I basically do what we call a confusion matrix, this actually tells us how well my model performed. So it basically maps my predictions against the reality. So we see here that I correctly predicted 114 died and 53 survived. But 20 who actually survived, I said they died. And 36 who died, I said they survived. So there's room for improvement here. Let's have a look at the tree. Ooh. That's a behemoth, right? Look at that. Let me just come out this so we can actually get a better look at how big that monster is. There's our decision tree. It's a bit big, isn't it? I mean, this is overfitting. I didn't specify a maximum depth of the tree, so the tree just carried on building itself. And that means the tree is very specific for the training data. This is overfitting. So we want to avoid that. So how can we avoid that? Well, what we can do, oops, a daisy. Let me just click on the right button. What we can do is we can actually tweak the decision tree's parameters. Let's try and reduce the depth of the tree, okay? And let's just set the amount of the depth to the same as the amount of features. Just a nice rule of thumb. So I set my max depth to 3, which you see here, and I test and score the model, and I get 80%. So I got 5% improvement just by removing the overfitting of the tree. Now, there are people out there, you can go online, you can go to Kaggle, for example, and you can see what other people have done with this, and some people have got very good, much better results than me, but you have to look at what they've done with the data, because everyone's just running the algorithm with a little bit of tuning, but it's the work that they do with the data up front that counts. It makes a difference between success and failure. Yeah, the confusion matrix, we can drop that. Let's have a look at the tree. That's how the new tree looks, which is a lot shallower, and a lot easier to explain to the kind of pointy-headed bosses. They'll be able to understand that. Before they would have just been, whoa, With this, you can actually read through it and understand how it's working. So that was that. Let me go back to the presentation. There we go. I've just got a couple of slides to wrap up. So, key takeaways. Scikit-learn and Jupyter Notebooks, free, easy to use, very good ways of getting started. There's lots of good books out there which will help you get started with Scikit-learn as well. And save yourself a lot of time when you download this stuff by just using the Anaconda distribution. I think feature engineering, this is a key takeaway of mine. Feature engineering is one of the most important skills that you can work with in data science. If you don't have that, your models aren't going to be very good. And domain knowledge is also key. Today, with Titanic, we all know Titanic, but if you're coming into a new customer, has a complicated domain, make sure you use the time to understand that first and speak to the domain experts. Split your data into training and test sets. Don't just test your model with the same data you used to train it. And don't forget that you can tweak hyperparameters of your algorithm. But try and understand why those algorithms give you better results. okay? Because otherwise, when things go wrong in production, you're not going to be able to give a good explanation to your boss. Tips for getting started in data science. This is my next to last slide. Become a data engineer. That's the easiest way. You guys are all like, you know, top-notch developers, right, and architects and that kind of thing. Become a data engineer. You know, get working with like things like Spark and Ray and Kafka and all that kind of stuff, and then you'll be working in the same kind of sphere as your data scientists. And when you're sitting together with them and working on the same projects, the cross-pollination, you know, you learn a lot. Learn Python or R. I find that like generally people with a technical or computing background prefer Python, and mathematicians prefer R. I don't know why. SQL is also useful to get your head around if you can't do it already. Learn some statistical models and methods. Take an online data science course. I recommend that. You can actually learn a lot from them. You know, the stigma against things like Coursera, Udemy, it's disappearing now. People are actually taking these courses seriously. Understand the data science process. It's not just about the machine learning, but it's also about the feature engineering and understanding the data. Join a meetup, of course, and play with Kaggle. It's the best. Set up an account with Kaggle. You can download the Titanic data set. You can process it, upload your results, and then compare what you've managed to do against other people and learn how they've got their results as well. So there you go. Thank you. I'm really happy to see so many people came today and that you were patient to sit in for the whole talk. So thank you very much for coming and enjoy the rest of your afternoon.